the material in those short sessions we had. So, Dr. J. Hebert, I think I'm saying your name right? Yes. Earned a bachelor's degree in physics from Lamar University in 1995, a master's degree in physics, 1999, from Texas A&M University, and a PhD in physics in 2011 from the University of Texas at Dallas, where he did cutting-edge research on the connection between cosmic rays, solar activity, weather, and climate. Very interesting. Dr. Hebert joined ICR in 2011 as a research associate, changed to research scientist in 2021, and is currently researching the post-flood ice age, topic very near and dear to me, and the dating methods used to assign ages to the seafloor sediments and the deep ice cores. Those are very important issues, as well as cosmology. Among other research endeavors, Dr. Hebert has authored several books and contributed to other publications, and we are excited to have you here. Let's welcome Dr. Hebert to our...
Well, thank you so much. I am delighted to be here this morning. I think I've got some information to share with you that you're going to find very, very encouraging. You know, when you go to, let's see, did it advance? Oops, it's not advanced. Oh, I'm sorry. There we go. All right. When you go to Genesis chapter 5, you see that the Genesis patriarchs were routinely living past 800 and 900 years of age. And many people have a hard time believing this. They think it sounds like something on a late-night TV infomercial. And I'm sorry to say that even some Christian apologists are pushing the idea that these ages are symbolic. And I completely disagree. The Bible is a history book. It is clearly meant to be understood as literal history. And don't let anyone kid you and tell you that you can't use the Bible's testimony as evidence. It is evidence, and you can use it. It's legitimate to cite the Bible as evidence for history. Now, since the Bible is God's Word, and since it's telling the truth about Earth history, we might expect some ancient people groups to have recollections of this great longevity. And we might even find some scientific confirmation for it. Now, before we get into possible scientific confirmation, there is a big, important question we have to first ask. Do we think that this longevity was natural, or do we think it was supernatural? I think it was natural. There's no indication in Scripture that there was anything miraculous or supernatural about this great longevity. There just seems to have been something about that pre-flood world and the immediate post-flood world that just enabled people to live to be really, really old. Now, if that's true, if this is potentially explainable scientifically, if it was natural, you're almost forced to conclude that the animals would also have experienced great longevity as well. And the reason for that is very simple. Okay, almost any conceivable mechanism that you can think of to explain greater human longevity would also have applied to the animals. Okay, a lot of people think that Adam and Eve, their DNA was perfect when God made them. Their immediate descendants would have had few mistakes in their DNA, and that was probably a big factor. Well, guess what? The animals didn't have any mistakes in their DNA either when God made them, all right? So if the DNA is part of it, then you would expect that for the animals. Likewise, maybe the environment had something to do with it. A lot of people suspect there may have been more oxygen in the pre-flood atmosphere. Well, guess what? The animals are breathing that same air, okay? Just about any mechanism you can think of to explain that greater longevity would have to apply to the animals as well. And that means we might expect to find evidence for this great longevity in the fossils themselves. So that's what we're looking at this morning. We're going to be looking at both historical and fossil confirmation of this great past longevity. We've got some subpoints under those main points. There's 4 ancient groups of historians I'm going to mention. But you might wonder, how on earth does a physicist end up doing longevity research? Am I out of my lane here? I mean, do I really have any business doing this? My first 12 years at ICR, I was doing Ice Age research, okay? That's what I spent most of my time on. So how did I end up on longevity? Well, as you know, at ICR, we've got a big push right now on developing a theory of biological design. And I've long had a fascination with fossil giantism, the fact that animals in the fossil record, many of them were very large. And even before I came to ICR, I was intrigued by this topic. I actually purchased a monograph on the subject called Scaling in Biology that was published around 2000. And there was some really groundbreaking work in there by a physicist named Jeffrey West and two biologists. Actually, the physicist did most of the work, but, I'm just saying. Okay, but the reason I was interested in this, they were trying to explain why are animal body parts the sizes that they are relative to one another, and why do animals why are they the sizes that they are? But they also got into a discussion of the mammal circulatory system, and they were able to explain design features of it. And so because our president, Dr. Randy Galuza, knew that I was interested in this, he asked me to investigate biological scaling. And so I worked on that, and it kind of just swerved into this longevity issue. I found a few things, some connections, and we went from there. So having given you that little intro, let's talk about some of this ancient historical evidence for greater longevity. Most of you have heard of the Sumerians' king list from Iraq. There's multiple versions of it, but it gives you the reigns of these Sumerian kings before and after the flood. And there's 8 of them before the flood. And if you compare those with the patriarchs in Genesis chapter 5, excluding Adam and Noah, you can see that the Genesis numbers are much more conservative. And so you might say, well, this is possible corroboration of greater longevity, but it looks like it's been exaggerated or embellished. But back in 1998, Raul Lopez pointed out that this could be the result of a translation error. If this was being copied by a scribe, and those original numbers were in base 10 instead of base 60, and the scribe didn't realize it, you would have gotten mistakes. And so the number of years, when you take that into account, is much closer to the biblical, the sum of the biblical numbers. And so this could be, not just general confirmation of greater longevity, but maybe very specific confirmation. The Jewish historian Josephus, he affirms that people used to live to be older, and he cites 11 other ancient writers corroborating this longevity. St. Augustine, the same thing in his book, The City of God, he affirms that ancient man lived to be longer. And he also said, interestingly enough, he said that men used to be larger than they are now. And you've got many Native American traditions that their ancestors used to live to be quite old. There was a well-known Native American lawyer and activist named Vine Deloria Jr., and he was very hostile to Christianity in his writings, but a lot of his stuff actually kind of incidentally confirmed what creationists would expect. And he said that there were Indian elders who many times had told him that in the old days, their people used to live to be hundreds of years old. And interestingly enough, Vine Deloria Jr. spoke very respectfully of some creation research done by a young earth creationist that was published in the Creation Research Society Quarterly in 1982 by a guy named Donald Patton. So we've got lots of historical confirmation of greater past longevity, but what about direct scientific evidence? We're going to be looking at fossil evidence here. And in order to understand the fossil evidence, we have to cover some background material. There's a field called sclerochronology. There's sort of a subfield called skeletochronology, and that's where you find these growth rings and hard body parts, and you count them. Okay, it is very similar to tree ring counting, but you're doing it on organisms. And they do it a lot on clams and oysters, bivalves, things like that, but they also do it on other creatures. And what they will often do is construct a growth curve that shows you how the animal's size over time varies. Okay, and we call this a growth curve. It's called a von Bertalanffy growth curve. If you're interested, that's the equation right there. That's the mathematical equation, and you can see there's this final size that it approaches, this maximum size, L infinity there, and that's the maximum size. Okay, and so what happens is you have this period of rapid juvenile growth. And then the growth starts to slow down, and then eventually you get to the point where there's no more growth, okay? At that point, the organism may get fatter, but it's not going to get taller or longer, okay? All right, so just keep that in mind. So there's more than one way you can construct these growth curves, okay? And you can do this for both living and fossil organisms, okay? One way is if you have a population of creatures. Let's say you have a whole bunch of shells of these particular clam, and you count the growth rings in them, and you also now know how long the clams were, then you can make a plot of those lengths versus age, and you can get sort of an average overall best fit, and that will give you the average growth trajectory for that organism. That's the best way to do it, because if you do it that way, you can do rigorous statistical analysis. Now, a lot of times you can't, okay? In a lot of cases, you may have to do it for a single organism. That's not ideal, but they do it a lot, especially for fossils, because sometimes you only have data from one fossil creature, all right? So what are we expecting here? Well, we as creationists believe that nearly all the fossils are from the Genesis flood. Now, there was a post-flood ice age that lasted for hundreds of years, and there was some catastrophic flooding at the end of that ice age. So we would expect there would be a few fossils from the ice age as well. Okay, but the vast, vast majority of these are going to be from the flood. Now, we know from Scripture that humans were still living to be very old after the flood, lifespans of 400 and 200 years. So we ought to expect to see evidence of greater longevity in both the flood and the Ice Age fossils. Now, where do the flood rocks end and where do the Ice Age rocks begin? Well, at ICR, we are firmly convinced that almost all of the rock record is from the flood. The boundary between the flood and post-flood rocks, we think, are between the Pleistocene and the Pliocene, okay, approximately, okay? Pleistocene, those are usually thought to be Ice Age. Those are identified as Ice Age rocks and fossils. And this is approximate. We're not saying it's this way every time. In some cases it may be a little bit higher or a little bit lower. But as a general rule of thumb, Pleistocene is where you're starting to get into the Ice Age fossils. Now, a creationist named Roy Holt many years ago pointed out that even some of the Pleistocene fossils might be from the flood, especially if you're looking at lower Pleistocene fossils. Now, if you look at upper Pleistocene, those are almost certainly from the Ice Age. Mid-Pleistocene, it could maybe go either way, okay? But the bottom line here is that we're expecting to see indications of greater longevity in both the flood and the Ice Age fossils. Now, the ideal thing to do would be to do an apples-to-apples comparison. If we could get growth data for a particular Genesis kind of animal and have that growth data for both the modern version and the ancient version and compare them, that's what we would like to do, okay? We can't always do that, but in some cases we can. Now, one complication here is that some of the best data we've got are coming from clams and oysters, bivalves. But bivalves, their longevity can be greatly affected by water temperature, food availability, and things like that. And even today, there's one particular clam that can live to be 400 to 500 years old, but it lives in a very high latitude, cold water, okay? As a general rule, cold water seems to promote longevity. You've also got the Greenland shark that lives in cold water. It lives to be very old. But so in some cases in today's world, cold water can explain greater longevity. But what I'm going to point out here in the examples I'm going to be showing you, cold water is not a good explanation, okay? Because both creationists and evolutionists would likely agree that these fossil creatures were living in relatively warm water. I've got examples from Antarctica, but the evolutionists think Antarctica at that time was warm during the Cretaceous and the Eocene. And as a creationist, I think those waters were warm as well. So in the examples I'm going to be showing you, cold water really isn't an explanation. So let's take a look at some of this direct fossil evidence. Some of the best evidence we've got comes from Crassostrea oysters. Now today, you've got Crassostrea virginica, which is also called the eastern oyster. It is very popular for seafood. But you've also got fossil versions of this Crassostrea oyster, and they have names like Crassostrea titan and Crassostrea gigantissima. Wow, I wonder why. Okay, well, I'm not absolutely 100% sure that's a Crassostrea oyster, but it is a fossil oyster. And you've got Crassostrea oysters that are humongous. Okay, one of them, as I said, is called Crassostrea gigantissima. There's another one called Crassostrea titan. And two evolutionists have said that the Crassostrea gigantissima is most certainly, or almost most certainly, the direct ancestor of today's Crassostrea virginica. That means it's the same Genesis kind. That means we can do a modern and fossil comparison. And somebody actually did that. Okay, and there was an evolutionist. This was published in 2001, and he was looking at Crassostrea oysters from North Carolina and Virginia, and also from California. Now, you might worry that if they're that far apart, is this a fair comparison? But they were within a relatively narrow latitude band, and more importantly, evolutionists think that the waters off the coast of California at that time were a lot warmer. So it's a more even comparison, even though you're looking at stuff from the Atlantic and Pacific. And here's what he found. Okay, this is a summary of his results. And this little growth curve right here was the modern assemblage. There was a modern assemblage of Crassostrea oysters, a whole bunch of them. They got that growth curve. And the lengths of these curves are not arbitrary. Okay, they stop at the maximum age that was in each assemblage. Okay, so in that modern group, none of the oysters lived to be more than 6 years old. You got an Ice Age group. They were living to be longer. Okay, the longest lived to be 9 years old. But then we get to these Miocene oysters that we think are from the flood, and they're living to be 20 and 23 years old. And I would hasten to add that these are absolute minimum estimates, okay? Because, first of all, remember, these creatures were killed in the flood. So that's just how old they were when they died. That still doesn't tell us the true lifespan potential. Another reason we should view these as minimum values is because according to the paper, some of these oysters were very crowded. The fossil assemblage was very crowded, and crowded oysters tend to have shorter lifespans than oysters that aren't crowded. All right, so that's very interesting, but that's not the only example. We've got other examples of Crassostrea oysters. Now, there was one fossil oyster called Crassostrea graphoides that they think they misclassified. Now they think it was Magellana graphoides. So we're not really worried about that one right here. But you can see that thing was huge, okay? And it, too, was living to be 40 years old, okay? But what I'm more interested in here is these other growth curves down here. Now, the curves labeled 1 are the curves you just saw in that other graph. Those are the two Miocene curves. The curves 3, 4, and 5, I believe, are also Crassostrea oyster growth curves, but they're from Mexico, Bangladesh, and some additional ones from the eastern seaboard, okay, North American eastern seaboard. Okay, and you can see there's a consistent pattern, okay? The Crassostrea oysters, the modern ones, they're just not living as long. They're not living as long, and they're a lot smaller than the fossil versions. Now, I believe curve number 5 is a modern-day Magellana clam, okay? That's interesting because, again, that gives us 2 examples, okay, where we can compare fossil and modern versions and see there's a dramatic difference in longevity. But this is not the only example. There were other studies. Someone did a study of Crassostrea oysters from the Pleistocene, the time around the American Revolution, the colonial era, as well as modern times from Maryland, Virginia, and North Carolina. And the Pleistocene oysters had much greater lifespans as a general rule. And this was published in the 2018 paper. And you can see here that from the Maryland oysters, there's a big drop in lifespan. Same for the Virginia oysters. The North Carolina oysters is not as clear, but there's a little bit of a drop there. And if you're interested in learning more about this, this was published in an open access paper at the Creation Research Society Quarterly. Those graphs I showed you are not in the paper. I included those graphs to make it easier to summarize the data, but most of this other stuff is in that paper. All right, so you've got long-lived Crassostrea oysters, but you've also got some very long-lived Antarctic clams. There's an island called Seymour Island at the tip of the Antarctic Peninsula. It's thought to be a very important place for southern hemisphere paleontology. And people have studied fossil clams on this island, and we're going to be looking at some from the Eocene first. Okay, and you can see here, these things are routinely living to be more than 100 years old, and they're not that big. Okay, they're not that big. Okay, these, the maximum size here is what, 140 millimeters? That's 14 centimeters. These are not big clams, but they're living to be very old. And if you remember the shape of that growth curve that I showed you it looks like their growth has not leveled off yet. These things may have still been growing when they were killed. And the authors said these are some of the longest lived clams ever documented from the modern or ancient world, and they describe this longevity as extreme. Now, that's not all. Okay, they also looked at Cretaceous clams from Seymour Island as well, and guess what? Some of these are living to be over 100 years old. Okay, you have 3 different genera, and I mean, these things are just, these are huge lifespans. And the authors of this paper said it is highly likely that individuals older than those reported are present in existing collections and virtually certain that they are present in the field waiting to be discovered. So these are not the oldest ones. There's ones out there that are probably older than this. There's even more data, okay? Also from Seymour Island, okay? They found an ammonite. Okay, it's a kind of weird-looking ammonite. Its shell looks like a giant paperclip, but they now believe it was more than 200 years old when it died. And Linda Ivany, who is one of the leaders in this field, said that scientists must therefore find ways to accept the reality of extreme longevity in this enigmatic animal. Okay, we got one more direct example. We have some very small, long-lived Jurassic mammals. Okay, so these are from the Jurassic, and there were some papers published, and 2 of the papers are open access. You can read them for free if you like. This one was published in 2020, and the authors examined these little Jurassic mammal critters. One of them is called Morganocodon, okay, a little cute little thing. But these are little bitty things, okay? They're like the size of a shrew. When we look at, none of them weighed more than 130 grams or had masses more than 130 grams. Well, what they did was they had these little bitty teeth, but they were able to use some very sophisticated X-ray microtomography to count growth bands in the roots of the teeth. And what they found is the Morganocodon was living to be up to 14 years old, and the other one, the Cuneotherium, was living to be up to 9 years old. Now, if you think about that, that's remarkable because these are little bitty animals, and little bitty animals don't normally live to be that old. Okay? There was a follow-up paper in 2024, and they were able to summarize all this data, and there were 7 little bitty Jurassic mammals that had extreme lifespans compared to mammals living today. Okay, those little colored squares, those are the lifespans of those 7 Jurassic mammals The black dots are the lifespans of living mammals today, and these are both in the wild, okay, not captivity, but in the wild. And you can see they are way above the trend line. That red line is the trend line for modern day mammals, and they're way up there, okay? They are clearly exceptional. And this is what one Science News article said. Recent work has shown that the first mammals in the late Triassic and early Jurassic lived much longer than similar-sized mammals today, up to 14 years old. If you compare that with today's shrews of similar body mass, some of which live to just over a year, this is a huge difference in lifespan. All right? So that's the direct evidence. Okay? That's the direct evidence. Now, I think right now would actually be a good time to take a break. Okay? This is a good stopping point. We'll come back and we'll get into the indirect fossil evidence, and there's a lot of that. And we'll get back to that after the break.
Great. Thank you very much, Dr. Hebert. Just a couple.
All right. Before we get into the indirect fossil evidence, I want to kind of give a little more backstory on this. How did I end up working on longevity research? Well, as I told you before, I've been interested in biological scaling, giantism, things like that. So even before I started working at ICR, I purchased this monograph, Scaling in Biology, and some of the work in there was really significant. And Jeffrey West and two biologists worked on this, and they had a scaling theory, okay, that basically assumes that the mammalian respiratory and cardiovascular systems are designed to be energy efficient. Now, sadly, they didn't give the Lord Jesus credit for that, okay? They said it was natural selection. And at ICR, we are very down on natural selection. We think it's mythical. We think it's fictitious. And we are working very hard on an organism-focused theory of biological design to replace it and to try to do biology like Darwin had never been born. Now, yeah, that's what we want. So here's something, though, that came up in this research. There's a really well-known rule in biology called Kleber's law or Kleiber's law that says that an organism's basically resting metabolic rate goes as its body mass raised to the 3/4 power. So in other words, bigger animals have higher metabolic rates, but it's not a simple one-to-one relationship. Okay, if you double the mass, the metabolic rate doesn't double, but it becomes 68% greater if you run the numbers. Okay, so they will often depict Kleber's law on what we call a log-log graph, logarithm versus logarithm scale. And when you do that, you get these straight lines that have slopes of 3/4 or 0.75. And it looks like this seems to be true over a wide variety of organisms, including unicellular organisms, cold-blooded organisms, if you will, and warm-blooded organisms. Now, here's what's really cool. West and his two colleagues, they derived Kleber's law. Okay, they derived it. They took conservation of energy. They took the assumption that the cardiovascular system was designed to be energy efficient, and they modeled the cardiovascular system as what they called a hierarchical branching supply network, where each vessel in the network branches into other vessels, which branch into other vessels, and they chose the radii and lengths of the blood vessels in such a way as to maximize the efficiency. And when they did that and turned the crank, they came out with Kleber's law, okay? And it's a pretty painful derivation, but I've got a paper that goes through it if you're interested. But here's where it really gets interesting, and for me it starts getting exciting. Then they took conservation of energy and Kleber's law, which they had just derived, and they turned the crank, and they got what we call an ontogenetic growth function of body mass as a function of time, okay? And their body mass versus time curve looks like this. And if you're interested, here's the equation. Okay, it's got an exponential function in there. Little m is just mass at any general time. Big M is the adult mass. Okay, so you can see what this curve looks like. So it's similar to the growth curves I showed you earlier, but instead of length versus time, it's body mass versus time. And they also showed that you could fit a lot of real biological data to these curves and get good results. Now, if you look at this curve, you'll see that the curve more or less starts to level off or flatten out right about there. And I'm going to call that T mature, the age of maturity. That's when it reaches its maximum body size. Well, they were able to do that, and they were able to show, and the math wasn't that hard, but they were able to show that that age at maturity is proportional to body mass raised to the 1/4 power. Okay, now that's interesting, but guess what? Even before they derived that result, biologists had long noticed this. Okay, you go back to the 1980s, there's papers and books, even before the 1980s, where they're noticing that these biological timescales in general seem to go as body mass raised to the 1/4 power. And if you're interested, I've got my ICC paper on this from 2023. It gives you some of those references if you want to go look them up. And by the way, it also has the derivation of Kleiber's law, if you're interested in that as well. So keep in mind that over the years, people had noticed that there were these tendencies for biological timescales to go as body mass to the 1/4 power. Now, there's also a ton of modern longevity research in living animals that show two big trends, okay? One of them is the longer you live, okay, the longer it takes you to reach adulthood. Or you could think about it the other way around. The longer it takes you to become an adult, the longer it takes you to reach full adult body size, the longer you live. That's a really strong trend that keeps showing up over and over and over again. Now, we also know just from general experience that larger animals tend to live longer than smaller animals. So let's start thinking about this. Does this make sense in light of that relationship between biological timescales and body mass? Okay, greater longevity is longer lifespan. That's a biological timescale. Larger adult body sizes, that means that's a larger adult body mass, capital M in that equation. And longer times to reach adulthood, that too is a biological timescale, a greater age at maturity. Okay, so what this means is, because of these relationships, evidence for greater ages at maturity and larger body masses are indirect arguments for greater longevity. Okay, now I think the larger body mass can probably explain a little bit of the extra longevity, but I think most of it's due to other factors, things like genetic entropy and changes from the pre-flood to the post-flood world. But here's the point, though. Again, let me emphasize this. Evidence for a longer age at maturity, greater age at maturity, delayed maturation, and larger body sizes are indirect arguments for greater longevity. So here's the question. Do we see evidence of these things in the fossils? You betcha. You betcha. We sure do. And I want to give a shout out to some creationists of years past, Donald Patton, Dr. Jack Cuozzo, and Greg Beasley. I couldn't find Greg Beasley's picture, but I would have included it if I could. These guys deserve a shout out because decades ago, they realized that delayed maturation ought to be associated with greater longevity. And Patton and Beasley also recognized that larger adult body sizes should go with greater longevity as well. I'm not sure if Jack Cuozzo reached that same conclusion, but he did conclude that if you're taking longer to mature, you ought to live longer. So here's the question. Do we have evidence? By the way, before I move on, Donald Patton, remember, Vine Deloria Jr., Donald Patton was the guy whose research Vine Deloria Jr. respected. He wrote an article in 1982 in the Creation Research Society, and even though Vine Deloria Jr. was really anti-Christian in his outlook, he thought pretty highly of the work that Donald Patton had done. So we've got evidence. Is there evidence for giantism and delayed maturation in the fossils? Well, you betcha. Okay, evidence of giantism is all over the place. You've got giant fossil penguins, giant fossil insects, giant fossil bivalves, clams and oysters, giant fossil turtles, giant fossil elephants, giant fossil camels, giant fossil kangaroos, giant fossil birds, giant beavers. I mean, we could go on and on. Okay, we could literally spend an hour on this one topic alone. There's rampant giantism all throughout the fossil record. Now, what about delayed maturation? Okay, well, again, we can count growth rings in these hard body parts, and you can do this. For instance, if you have a fossil shark vertebra, there are growth rings that you can count. Okay, likewise, there are things called osteoderms in alligators and crocodiles that have these growth bands that can be counted. And here, the threshold for evidence is a little bit lower. We don't really need the entire growth curve. If we can just get enough of the juvenile part of the growth curve to show that it was taking a long time to mature, then you've showed it's delayed maturation. Okay, even if you don't have the full shape of the curve, if it's obviously taking a long time to mature, that is indirect evidence for greater longevity. And there are what are called allometric equations. There are these average relationships between the sizes of individual body parts and the size of the whole body. So, for instance, as an example, if you know the length of a crocodile or alligator's head, you can estimate its body length. Same thing for sharks. Okay, if you make an assumption about what the body type looks like, if you have the radius of the vertebra, you can estimate what the length of the shark was. So now when you do these, you often will get growth curves that sometimes are a little bit herky-jerky looking. Okay, I mean, that's just the way it is. You're making approximations. They aren't necessarily nice and smooth like the clam and oyster curves, but we're going to see some examples here. All right, what about evidence of delayed maturation? We see this in fossil fish, okay, that and giantism. The coelacanth, okay, was thought to be a living fossil for many years. Today, they never get more than 1.9 meters long, but there was a paper recently that showed that they tend to live to be about 100 years old. Well, guess what? You've got fossil coelacanths that were about 5.3 to 5.4 meters long. How long did they live? All right. The evidence is even stronger when you look at sharks. We've got actual growth data from sharks. And of course, the megalodon, the giant shark, that's one well-known example. There was actually a fossil vertebra they had. This is not it. This is another shark vertebra, but I'm just using that for illustrations. This particular vertebra had 46 growth bands. They were evenly spaced. And when they're evenly spaced, that means it's growing at a constant rate, which means it's still on that linear part of the growth curve. It's still a juvenile. So stop and think about that for a second. You've got a 46-year-old juvenile shark. Now, they assumed it had a body type like that of a great white shark, and conservatively, that would have mean it would have been 52 feet long. And you can extrapolate that growth rate, and you can see that at a minimum, it would have taken more than 89 years to reach maturity. Okay, now, remember, it has to be more than 89 years because you know the growth has to slow down. It's got to slow down, and any slowdown in the growth is only going to increase the age at maturity. Now, when they did this calculation, they're assuming that each growth band represents a year. Now, to be fair, that's not airtight. Okay, there are some sharks where they found the growth band can represent 2 years, and sometimes you have a shark vertebra where the growth bands differ in different vertebrae from the same shark. Okay, but this is the assumption they usually make, and they took the smallest vertebra they had to be as conservative as possible. And if you do that, you're looking at more than 89 years to reach maturity. Now later, there was a more recent paper where they said, no, we think it was more like a lemon shark, That changes the numbers a little bit, but it's still taking more than 70 years to reach maturity. By any standard, the megalodon was taking a long time to reach maturity, and that is an indirect argument for greater longevity. There's another genus of fossil shark called Tychodus. It was really big, but for a fossil shark, it wasn't that big. It was only about 10 meters long, like 30 feet, okay? Well, there was a paper not too long ago where they said they think it had a body like that of a porbeagle shark. And so if you assume it's got those proportions, you can show that it would have probably taken around 63 years to reach maturity. That's not the only example. There is a giant fossil shark from Italy where they've got part of the growth curve. They've got a little bit of curvature on that growth curve, and they estimate it would have taken 64 years for this shark to reach 95% of its adult body length. Now, to put that number in perspective, great white sharks in the North Atlantic will often take maybe 33 years to reach 95% of their full adult size. All right, so again, these sharks are taking a long time to mature. Now, that's all the growth data I've got for the sharks, but we also have evidence that sharks that are still around today were once much larger in the past. You've got this shark called the snaggletooth shark, Hemipristis elongata. The longest length that's ever been recorded is 12.5 feet, and most of them are not that long. But you've got fossil versions of this shark that they think were around 20 feet long. Okay? The thresher shark, you know, the sharks with those weird-looking fin tails, they've got fossil versions that they call giant threshers, and their teeth, the teeth of these fossil thresher sharks have been described as highly enlarged versions of thresher teeth. Well, it doesn't take too much of a stretch of imagination to think that if the teeth are bigger, the animal itself may have been bigger as well. You've got the blunt-nosed six-gill shark, okay? And they've also got a Neogene version from the Miocene, and they gave it the name Hexantius gigas, gigas being derived from the word for giant. And these paleontologists said the only convincing difference we can see between it and the one that's around today is body size. This thing was just bigger. So I'm suggesting that these larger body sizes and indications of greater ages at maturity are indirect evidence that these fossil sharks were living much longer than most modern-day sharks today. And I've got a paper. It's online. If you want to read this paper, it's open access. It was published in the Creation Research Society Quarterly. But that's not the only example we've got. We've got evidence of giantism and delayed maturation in fossil reptiles. You have what are called terror crocodiles. You have the Sarcosuchus imperator that was more than 30 feet long. Okay? It's this giant crocodilian-like creature. There's another one called the Deinosuchus that's pretty similar in body size. They're about 10 meters, around 30 feet or so. And those there you can see their lengths compared to today's saltwater crocodile. Okay, so they are significantly larger. Well, there was a 1999 paper where the scientists actually constructed growth curves for Deinosuchus. They had fossil data from Montana and Texas, and they constructed those growth curves. And I've reproduced their data as best I could. And for comparison, I've got the growth curve for today's American alligator. Now, to make a one-to-one comparison, I went ahead and extended the growth curve for the alligator out to 50 years. But most alligators and crocodilians today don't live past 30. There are some exceptions. Every now and then you might find one that's 70 years old, but most of them don't live past 30. So you've got these fossil crocodilians that are still growing at 50 years of age. Okay, they're already living longer than most crocodilians today, but they're still growing. And Jack Horner and two other scientists published a paper in 2004 where they published a smoothed curve for that Deinosuchus curve. Now, they didn't give the equation for the curve, but I was able to reverse engineer it. And that solid and dashed line up at the top, that's their extrapolation. They didn't extrapolate, but I went ahead and extrapolated. And the triangles and the diamonds are my reconstruction of their data. Okay, I couldn't get the raw data. I reconstructed it from the figures as best I could. But you can see there's a good fit. And what's really remarkable about this is that it looks like this thing may have still been growing at 70, 80, 90, maybe even 100 years of age. Now, admittedly, every time you extrapolate, that's a little bit risky, but it's not far-fetched to think this thing could have been taking a very long time to mature. Ditto for the Sarcosuchus imperator. There was a paper published in the journal Science in 2001 where they concluded that it took 50 to 60 years to reach maturity. Now, you might quibble and say, well, those aren't creatures that are around today. Deinosuchus and Sarcosuchus, some might argue these are not related to today's crocodiles, and admittedly, they did have some unique anatomical features. By the way, some people have speculated that Deinosuchus might be Leviathan, and Sarcosuchus as well. Deinosuchus is probably a better candidate, but they've both been suggested as candidates for the biblical Leviathan. Well, do we have examples of creatures that are still around that could be giant crocodilians? Well, maybe. For instance, today you have gharials and caimans. Caimans are like they're crocodile-like, but they have rounded, more blunt snouts. Gharials have very elongated, narrow snouts. And yet you have a fossil creature, one's called Gripposuchus, the other's called Ethicodon, that had very narrow, elongated snouts, just like today's gharials. Now, evolutionists claim this was convergent evolution, okay? They just happened to evolve the same distinct feature multiple times over millions of years. But what if Gripposuchus and Ethicodon are simply giant, long-lived gharials? Okay, that larger body size would be an indication of greater longevity. Not only that, you can make the same argument with Purosaurus. Okay, was it just a giant, long-lived caiman? Now, here's I'm going to make another argument here. These crocodilians, these fossil crocodilians, had body sizes comparable to that of Deinosuchus and Sarcosuchus imperator. It's a good bet, it's not certain, but it's a good bet they were also taking a very long time to mature as well. So we've got some pretty strong evidence here that these crocodilians were living a long time. Both the large body size and the delayed maturation would be evidence for that. Now, an objection someone might throw out is that, well, large dinosaurs grew quickly. In fact, if a memory serves, I think this was an objection that was actually raised to me at the 2023 International Conference on Creationism when I first presented some of this research. And the argument is, look, you have these large dinosaurs. They're huge. You would expect them, just by virtue of their body size, to have long lifespans. And because delayed maturation, long ages at maturity are associated with it, you would expect them to take a long time to reach maturity. And yet, for many years, it's been gospel, or accepted as gospel, that dinosaurs matured very quickly, including the sauropods. There was a paper that claimed the Apatosaurus reached maturity in just 15 years. And if you believe that, that means the maximum growth rate would have been 5,000 kilograms per year. Also, people were claiming that the Tyrannosaurus rex took 25 years to reach maturity. Okay, so that would seem to be an objection to what I'm arguing. You would think these really big animals would take a longer time to mature. Well, guess what? In 2013, Nathan Myhrvold, who's been described as one of the most curious people on the planet, he's something of a savant, but he actually published a paper called Revisiting the Estimation of Dinosaur Growth Rates, and he was very critical of these dinosaur growth studies. And he said many previously published results in dinosaur growth studies were obtained using methods that deviate from accepted statistical practices or irreproducible due to lack of published data or methodology. Ouch. Okay. But there were two studies he did not criticize. One was by a lady named Woodward, Holly Woodward, and in her study she estimated the Apatosaurus would have taken 70 years to reach maturity. And then she did another study with a scientist named Lehman who figured that the alamosaurs would have taken 45 years. And even in those examples, they didn't have all their, they didn't have as much data as you would like, but those numbers seem a lot more reasonable. Well, guess what? Wouldn't you know it? But this week, Holly Woodward, Nathan Myhrvold, and the famous paleontologist Jack Horner just came out with a paper saying that T-Rex actually took 40 years to reach maturity instead. Okay, I don't know about you, but I think that's exciting. And I have a feeling they're going to find that these other previous studies were flawed, that these large dinosaurs were taking a long time to mature, just like you would expect. We've also got evidence of delayed maturation in fossil birds. Okay, here's a quote from a 2023 Nature paper where Kevin Padian says the first birds took several years of development to reach skeletal maturity, but today's birds can do so within a year or less. And many of those birds do so within a lot less than a year, like weeks to months. All right, so you're looking at, in many cases, weeks to months today to reach maturity compared to years to reach maturity for these fossil birds. And the Archaeopteryx is one example. There was a study published where they think it took 2.7 years to reach maturity. And even that's not airtight, because if you look at this growth curve that they've constructed, the data, okay, those diamonds you see, they don't have any adult Archaeopteryx specimens. Those are all juveniles. So when you get into the adult part of the curve, they're kind of guessing. Okay, so it might even be more than this. Okay, but we got good reason to think these fossil birds were taking a very long time to mature. Also, not that long ago, well, actually it was about 7 years ago, two evolutionists suggested a possible reason why fossil birds might have teeth, even though none of today's birds have true teeth. Now, there are some birds that have what you call pseudo teeth, but no birds today have true teeth. And now, evolutionists have made a big deal about this. They've said, well, this is evidence for evolution. The reason fossil birds had teeth is because they came from reptiles which had teeth, and then over time they just lost their teeth due to mutations and natural selection. Well, guess what? These two evolutionists suggested maybe the reason fossil birds had teeth but today's birds don't is because they took longer to incubate. Okay? For instance, in reptiles today, it might take at least 40% of the incubation time for teeth to start developing. Now, we're not saying that birds came from reptiles, but suppose they had a comparable development schedule in the egg. Okay? If you have a shortened incubation time, there might not be time for teeth to develop. Okay? There might be epigenetic mechanisms in there that instruct the developing bird to don't waste resources on teeth. You don't even have time to make them. Do something else. And why am I so pumped about that? Why did I get so excited when I saw this paper? Well, guess what? Longer incubation times are associated with greater longevity. When I talk about delayed maturation, it's not just delayed maturation after birth or after hatching. Maturation times before birth and hatching are also associated with greater longevity. So the fact that these fossil birds had teeth, rather than being evidence for evolution, that could actually be indirect evidence to corroborate the Bible's claim that people were living to be very old. Okay, the animals were living to be very old and the people were as well. And finally, we've got evidence of delayed maturation in fossil mammals. Okay, remember these cute little mammals I showed you earlier? Well, the scientists who examined the data, they had sufficient data to show that 4 of them were taking a very long time to reach sexual maturity. Okay, again, those colored bars, those are the estimates for the fossil critters. The black dots, those are for mammals living today as a function of body mass. And you can see they're way above the trend line. They're taking a much longer time to mature sexually. Now, there's another reason this ought to make you excited, because if you look at the data in Genesis chapter 5, it strongly suggests that humans were also experiencing delayed sexual maturation. The youngest 2 ages in Genesis 5 at which a patriarch is listed as having a son is 65. Okay, that's the youngest age. Now, I don't know about you, but I don't think people were hitting puberty at 12 and 13 and everybody was just choosing to wait 50 years to get married, okay? I just don't think that's reasonable, okay? In fact, most of these ages are even higher than that. One of the ages that Lamech, the age of his son occurred when he was 102, okay? 182 years old. Okay, so 65 is way down at the bottom. Okay, so I will grant you the Bible does not explicitly say these are firstborn sons, but those 65 ages, those two ages there are so low compared to the others, it looks like this was early on in their reproductive lives. So this Genesis 5 data strongly suggests that humans were experiencing delayed sexual maturation, and that makes sense. Delayed maturation is something that goes along with greater longevity. And by the way, this is not something that somebody who was faking it would have thought to do. If somebody was just making this up, they would not have thought to include that detail. But there's one other thing. We've got good reason to think that Ice Age animals, particularly mammals, got smaller at the end of the Ice Age. We know that bison got a lot smaller. They actually shrank. And you can actually see websites that talk about the incredible shrinking bison. Well, they've known this for a long time, okay? There is very strong evidence that mammals at the end of the Ice Age got smaller. In fact, there was a 1981 paper where the scientists said this dwarfing of fossil mammal lineages at the end of the late Quaternary was probably worldwide. Now, that's over 40 years ago, okay? So this scientist is saying, based on, and he cites a bunch of other papers for this conclusion, that it looks like mammals all over the world got smaller at the end of the Ice Age. Now, I don't care if you're an evolutionist or a creationist. If you're trying to explain Earth history, that's an important clue. That's something you need to explain. That's a big deal. Now, does this possibly make sense biblically? Well, we know that human longevity was dropping during the Ice Age. From Genesis 11, it's a good bet animal longevity was also decreasing. And because of the link between body size and longevity, it's a good bet that animal body sizes were getting smaller as well. And so I've got an online paper. It's open access. You can read it. It's in the Journal of Creation, Late Pleistocene Body Size Reduction, Evidence of a Post-Flood Decline in Longevity. But that's not all. There's also evidence that other creatures got smaller as well. People used to use the South African tick shell to make jewelry, but here is a paper from 2007 asking the question, why were the shells of mankind's earliest ornament larger in the Pleistocene than in the Holocene? Okay, why did they shrink after the Ice Age? You've also got evidence from South Africa that granite limpets, South African fur seals, and a particular kind of tortoise called ungulate tortoises, they got smaller too. And there's also reason to think that monitor lizards got smaller as well. The gray monitor lizard right there, that is today's Komodo dragon, which is the largest living monitor lizard. The one labeled number 2 is the next largest one. But 3A and 3B are size estimates for a Pleistocene monitor lizard. So it looks like not just the mammals, but other creatures got smaller as well. And that is an indirect argument for decreasing longevity, like we would expect biblically after the flood. So I hope this information has been an encouragement to you. Our former president, Dr. John Morris, he used to love to say, it's a great time to be a Bible-believing Christian, and it really is. If you want to learn more about this, we've got lots of popular level articles on our website. You can just do a search for longevity. You'll pull up all kinds of stuff. But if you want to get into the technical articles, if you go to the menu at the top of our page, you hit on publications, then you pull down, there's a drop-down menu that will give you technical papers, and then you get another drop-down menu that goes to past articles, and there's a whole bunch of these articles up at the top. They were published very recently, and you can read them for free, no charge. And also, we've got our bi-monthly magazine, Acts and Facts. I think most of you are already signed up for it, but if you aren't, we've got cards. You can sign up for it. This is our gift to you. It's paid for by our donors, and every 2 months we've got articles dealing with important issues in the creation evolution controversy. So I think that's what I've got, and I think now we can open up for Q&A.
Yes, thank you, Dr. Hebert. And those resources are on the table in the corner
Right.
back over here. No charge. Feel free to take it. And Acts and Facts. And this issue, I think, is about dinosaurs, correct?
Yes,
Yes.
the lead article is about dinosaurs. That's
All
correct.
right. And Dr. Hebert will be joining us for a lunch at the Fred Meyer Burlingame. If you have comments, you might save them for that time. And this is our question and answer time. If your question starts with the words, "This is really more of a comment," then please save that comment for lunchtime. So please make your way up front if you have a question. If you don't mind making your way up front, please. We hopefully won't have too long of lines. We'll start over here with Craig.
All right, I got a question over here.
Sure.
So with animals, there's a direct correlation between size and length of life. What about the human connection? Do you think that those old ages of the early patriarchs also indicate they were larger than modern humans?
I knew that question was coming. Okay, I knew that question was coming. Okay, are we suggesting here that possibly pre-flood humans were larger than today's humans? Folks, I'm having a hard time avoiding that conclusion. I really am. I know that might be controversial, but I think that's a possibility we've got to seriously consider. Now, please understand, that I'm not denying that the Nephilim were abnormal. Okay, the Bible talks about the Nephilim being giants. That was obviously something supernatural because of the sons of God. That's a totally separate issue. But could it be that normal humans in the pre-flood and immediate post-flood worlds were larger than today's humans? And I think it's possible. And by the way, that's exactly what Augustine said in The City of God. He said, yeah, people used to be bigger. The giants were bigger than everybody else, but normal humans used to be bigger as well. There's some artifacts out there that look too big to have been used by normal-sized humans. And there are multiple ancient sources that claim that normal post-flood humans were giants. Normal human post-flood humans, okay? These are some of those sources. In fact, the Shawnee Indians have a tradition that I'm going to read to you. They, the Shawnee, suppose their ancestors to have been much more perfect, both in intellectual and bodily formation, than the present race. They were of very large stature, both men and women, attributed in part to their abstinence from sexual intercourse during the early years of life. Now that really gets my attention, because that sounds like delayed sexual maturation, right? Which is something that goes along with greater longevity. In those days, the men at 100 years were equal to those of the present race at 70. A gradual degeneration has at last brought them to their present state and is now working imperceptibly among all the Indian tribes. Even in the mainstream paleontology, you will hear them occasionally use words like giants, okay? Lee Berger, he did an interview. Now, I know Lee Berger exaggerates, so you got to keep that in mind, okay? But I think there's reason to think that might very well have been the case. And I don't want to be dogmatic about it, but I think it's quite possible that normal humans before the flood were larger than we are. Yes.